Okay, so let's apply this now to our if we have a projectile, starting with projectile, or you might say projecting it or launching it with 0 launch angle. Usually if you launch something, it launches upwards at an angle, like if you think Angry Birds. But you can actually, if you've ever played Angry Birds, you can launch a bird at a 0 launch angle as well. Let's just, oh heck, why don't I just draw it? There's our little slingshot right there, okay? And then if you pull the bird, there he is in there, you pull it straight back, it will launch horizontally. Okay, now if you pull it back and down, it would launch up. We have 0 launch angle. So this theta right here equals 0 degrees. So if we have 0 launch angle, what does that mean about the initial x velocity and the initial y velocity? Well, the initial x velocity, and I'll write this in black here, initial velocity in the x is what we have right here. That's the initial velocity of whatever direction it's pointing. That is the whole magnitude, you might say, of the velocity of that bird or that object being launched, times a cosine of theta. Okay? Times a cosine of theta. So that, oops, I should make that black. That is initial velocity, you might say, of the magnitude times the cosine of theta. Well, if theta is 0, the cosine simply equals 1. So in this case, if theta is 0, the initial velocity in the x direction equals the whole initial velocity that is being launched at. Let's contrast that now against the initial velocity in the y direction. Well, look at this for a minute. This bird is being launched out horizontally. Is there any y component of this launch at all? What's the initial velocity in the y direction? That's kind of bad right there. What is that? You can see that that red vector, velocity vector, has no vertical component of all. So the y component of that is going to be 0 meters per second. So initial velocity in the y direction, if we want to prove it, is initial velocity times the sine of theta. Okay, well, the sine of theta, if theta is 0, the sine of theta is 0. So that winds up being 0. So if we have 0 launch angle, that is theta equals 0 degrees. That means the initial velocity in the x direction is the whole initial velocity, and the initial y velocity, that is the velocity in the y direction, is equal to 0. There is no vertical component of it at all. So with that assumption, if we are launching something at 0 angle, here's what our equations become. This right here, oops, sorry. You can think of that as x final is x initial plus initial velocity times time. But there's no acceleration. Plus 0, or you might say plus 1/2 at squared. There is no acceleration in the x direction, so that goes away. That's assuming there's no acceleration in the x, and the y direction has is negative 9.81. What's this right here? Our final y position is our initial y position plus negative 1/2 gt squared. Well, what happened to this part right here? Why didn't this that was in there too, right? If you recall that equation. Yf equals yi plus initial velocity in the y direction times time plus 1/2 times acceleration in the y direction times time squared. Look familiar? Okay, why did this whole center section drop out? That dropped out because there is no, at a zero launch angle, there is no initial velocity in the y direction. That goes completely away. So what we're left with is what we have up above right here. We have acceleration in the y direction, but no initial velocity in the y direction. Over here, our second equation, our initial velocity in the x direction is going to be constant. Again, we're ignoring friction, but it's not going to change in the x direction. Our initial velocity in the our velocity in the y direction, we would say is VIY plus negative GT, or plus AT. But since the initial velocity in the y direction is 0, that just simply goes away. I'll write the original equation right here. VFY equals VIY plus acceleration in the y direction times time. Okay, there's your acceleration, there's your time, there's your V final in the y direction right there. But the initial velocity in the y direction went away, because if there's 0 launch angle, then that means there's no y component of the original velocity. Okay, and finally, let's look at our third familiar equation. Once again, since the final velocity in the x direction squared equals the initial velocity in the x direction squared, I should say x right there, that means the x velocity is always going to be constant. It will be the same whether it just left the you might say the slingshot, so to speak, or the bullet just left the gun, or whatever it is. The x component will be the same. It will be constant. The y component will be changing, however, because the y has gravity. It has acceleration of gravity to it. So if we take final velocity y squared equals initial velocity of y squared plus 2 times acceleration in the y direction times displacement of y. Again, our initial velocity in the y direction is a 0. So that goes away. So what we're left with is simply what we have above right here. Again, you can think of the acceleration as minus 2gy or plus 2ay delta y. But again, the acceleration in the y direction is negative 9.81 meters per second squared. So these are going to be our main equations that we use for projectile motion. And as we have them right here, this only applies to projectile motion with 0 launch angle. You're shooting something out horizontally only. Later on, we'll get to talking about what happens if we have an actual launch angle and something is launched up. But for right now, let's use these equations right here, and let's look at a few examples.